The first atoms formed during a period known as recombination, which occurred about 380,000 years after the Big Bang. The universe was originally a hot, dense plasma in which protons, neutrons, and electrons existed in a chaotic state. In this extremely high-temperature environment, particles were constantly colliding with enough energy to prevent the formation of stable atoms. As the universe expanded, it began to cool, allowing these particles to lose energy and eventually combine to form the first neutral hydrogen atoms. At this turning point, when the universe cooled to a temperature of about 3,000 degrees Celsius, protons and electrons came together in a process known as recombination. Negative electrons were absorbed by positive protons, causing a significant decrease in the density of free electrons. This transition allowed photons, light particles, to travel freely through space for the first time, creating what's known as microwave background radiation. This glow has persisted since childhood, a sign of warmth, the birth of peace. The structure of hydrogen atoms is important because they make up most of the matter in the universe. But in the first few minutes of the universe's existence, helium also came into existence through a process called Big Bang nucleation. This process allowed protons and neutrons to combine to form helium nuclei, resulting in a universe composed primarily of hydrogen and helium. These elements served as the building blocks of stars and galaxies, eventually leading to the complex structures we see today. As stars formed from clouds of gas composed mostly of these first atoms, nuclear fusion produced heavier elements. This iterative process of stellar evolution and supernova explosions laid the foundation for the rich diversity of elements necessary for the formation of planets and life itself. The journey from the first atoms to the elements that make up everything around us is evidence of the dynamic evolution of the universe. Primitive nuclear fusion involves the formation of light elements in the first minutes after the Big Bang, i.e., between 3 and 20 minutes after the creation of the universe. During this short time, the universe was so hot and dense that nuclear reactions between protons, neutrons, and other particles were possible. The main elements used in this process are hydrogen, helium, and small amounts of lithium and beryllium. In a wider and colder universe, protons and neutrons begin to combine through nuclear fusion reactions. In the beginning, most of the universe consisted of free protons and neutrons. When the temperature drops to the range required for nuclear interactions, these particles begin to fuse. The most important reaction is the formation of helium from hydrogen. The combination of two protons creates a deuterium nucleus, a type of hydrogen containing one proton and one neutron. Other reactions allow deuterium nuclei to combine with more protons and neutrons to form helium nuclei. It is estimated that by the end of the first nuclear fission, about 75% of the world's natural elements had become hydrogen, about 25% helium, and lesser amounts of lithium and beryllium. These light elements became the fundamental building blocks for stars and galaxies that appeared later in the history of the universe. The relative content of these elements predicted by the theory of primordial nucleosynthesis agrees remarkably well with modern observations, confirming the accuracy of our understanding of the early universe. The importance of primordial nucleosynthesis cannot be overemphasized. This not only provides insight into the conditions of the early universe, but also lays the groundwork for the formation of more complex elements through stellar processes millions of years later. Understanding these processes helps scientists unravel the history of the cosmos and the origin of the matter that makes up everything we see around us. Hydrogen and helium became the predominant elements formed after the Big Bang due to a combination of factors related to the nature of nucleosynthesis and the conditions that existed in the early universe. The universe was originally a hot, dense medium filled with elementary particles, primarily protons, neutrons, and electrons. As the Earth expanded and cooled, conditions became favorable for the formation of atomic nuclei. During primordial nucleosynthesis, which occurred within the first few minutes after the Big Bang, the temperature and density were just right for protons and neutrons to undergo nuclear fusion. Protons, which are the nuclei of hydrogen, were the most abundant particles at this stage. Neutrons, although very small, also play an important role. It combines with protons to form deuterium, a type of hydrogen. The stability and simplicity of the hydrogen nucleus, with only one proton, allows it to have tremendous power. As conditions continue to change, deuterium nuclei fuse together to form helium nuclei, which contain 2 protons and 2 neutrons. Most thermonuclear processes are driven by strong nuclear forces that bind protons and neutrons together in the nucleus. In the hot, dense environment of the early universe, helium formation was favored because, when 2 protons and 2 neutrons combine to form a helium nucleus, it is a more stable configuration than separate protons and neutrons. As a result, about 75% of normal matter was in the form of hydrogen, and about 25% in the form of helium. Only trace amounts of lithium and beryllium were produced because of their higher binding energies, making their formation less favorable under the conditions of the early universe. The dominance of hydrogen and helium laid the foundation for the evolution of stars and galaxies. These light elements served as the primary fuel for stellar nucleosynthesis, enabling the formation of heavier elements within stars through processes that would unfold over billions of years after the Big Bang. By understanding why hydrogen and helium were the predominant elements, scientists are discovering crucial clues about the very nature of cosmic evolution and the building blocks of matter. The first elements, primarily hydrogen and helium, began to appear a few minutes after the Big Bang, namely during a process known as primordial nucleosynthesis. This process occurred about 3 to 20 minutes after the explosive expansion of the universe began. During this short period of time, the universe cooled enough for protons and neutrons to combine to form atomic nuclei. Immediately after the Big Bang, the universe was an extremely hot and dense environment filled with fundamental particles such as quarks, gluons, and electrons. As the planet expands, the temperature decreases. As the world cooled to 10 billion degrees Celsius, conditions became favorable for nuclear interactions. Protons and neutrons produced by quarks began to combine to form lighter nuclei such as hydrogen and helium. After the first nuclear fusion was complete, most of the universe was hydrogen, which was 75% of everything, and helium, about 25%. In addition to hydrogen and helium, several light elements such as lithium and beryllium were created. This initial composition laid the foundation for the subsequent formation of stars and galaxies. As the universe continued to expand and cool, about 380,000 years after the Big Bang, electrons joined with the nuclei that formed in a process called recombination, resulting in neutral atoms. This moment was marked by the release of the cosmic microwave background radiation, which for the first time allowed photons to travel freely in space. Thus, the fundamental elements arose a few minutes after the Big Bang. The formation of neutral atoms occurred hundreds of thousands of years later, marking distinct stages in the evolution of the early universe. Dark matter played an indirect but crucial role in the formation of the first elements in the universe. Although dark matter does not interact with electromagnetic forces and is therefore invisible and undetectable by conventional means, it exerts a gravitational influence that affects the large-scale structure of the cosmos. This gravitational pull facilitated the process that led to the formation of the clumps of matter necessary for the subsequent development of stars and galaxies. After the Big Bang, the universe began to expand and cool. Matter, mostly in the form of hydrogen and helium, created during primordial nucleosynthesis, began to stick together under the action of gravity. Dark matter, which is believed to be about 26% of the mass energy of the universe, played an important role by providing the additional gravitational attraction necessary for the fusion of ordinary matter. This resulted in gravity wells that contributed to the formation of the first structures in the universe. These clots of matter eventually became dark matter halos, within which ordinary matter could accumulate. Over time, as the density of matter increased, regions of gas became dense enough to collapse under their own gravity, giving rise to the first stars. Nuclear fusion in these stars produced heavier elements, which later became available to form new stars and planets. In this sense, dark matter served as the scaffolding that shaped the early universe and allowed the complex structures we observe today to emerge. Although dark matter has no direct effect on element formation, its gravitational interaction is fundamental to the processes that lead to star formation and the subsequent synthesis of heavier elements in the star's interior. Understanding how dark matter works can help us understand the entire evolution of the universe and the origin of the elements that gave rise to galaxies, solar systems, and life itself. To understand the formation of the first atoms in the early universe, we need to look at the time just after the Big Bang, about 13.8 billion years ago. In the past, the planet was a very hot and blue place, with temperatures reaching millions of degrees. At this time, energy was too strong to allow the formation of stable atoms. Fundamental particles, such as quarks, are created and destroyed. When the universe began to expand and cool, about 378,000 years after the Big Bang, a massive event called thermonuclear fusion occurred. Electrons and protons combined to form neutral hydrogen atoms. Now the world is bright, and light can travel freely. However, hydrogen, being a simple molecule, is just the beginning. Over time, under the influence of gravitational forces, these hydrogen atoms began to stick together, eventually leading to the formation of the first stars and galaxies. Nuclear fusion began inside early stars, producing helium and traces of other light elements such as lithium and beryllium. As the life cycle of these stars came to an end, they exploded in supernovae, scattering their enriched innards, primarily hydrogen and helium, across the cosmos. It was during these cataclysms that more complex molecules began to combine, giving rise to the first molecular compounds. This process laid the groundwork for the formation of stars and planets, and more familiar molecules such as water and carbon dioxide gradually emerged. The formation of the first molecules was not only a monumental step in chemical evolution, but also paved the way for the development of more complex structures that eventually led to the universe as we know it today. These early molecular formations played a crucial role in the origin of life, stars, and everything else in the cosmos, connecting the simplest particles into the tangled web of existence we see around us now. Interstellar dust plays a critical role in the formation of complex molecules in space. Dust, made up of tiny particles mostly of carbon, silicate minerals, and ice, exists in the vast regions between stars. Although water makes up only a small fraction of the total mass of the universe, it acts as a crucial catalyst for the formation of more complex substances, marking an important step in the chemistry of the cosmos. As the universe evolved, the first stars and galaxies formed from primordial hydrogen and helium. Over time, stars formed heavier elements through nuclear fusion. When stars die, they dump enriched material into the interstellar medium, filling it with various elements. Interstellar dust particles are places where atoms and molecules can gather and interact. This particle density allows for chemical reactions in which simple molecules, such as hydrogen and carbon compounds, begin to combine and become more complex. One of the most interesting results of this process is the production of simple organic compounds. These include amino acids, which are the building blocks of life. Observations of dense molecular clouds, areas rich in dust, have revealed an abundance of these organic molecules, showing that the beginnings of life may well have originated far from Earth, in the cold and dark expanse of space. Surface reactions facilitated by interstellar dust allow these complex molecules to form and even evolve into larger structures. The combination of stellar evolution and the influence of interstellar dust allows us to trace a remarkable path from simple atoms to complex molecules. This transformation not only contributes to the chemical richness of galaxies, but also serves as an important link in the potential emergence of life, reminding us that the building blocks of existence are often forged in the quiet, dark regions between stars. Detecting complex molecules in space is a fascinating endeavor that combines advanced technology with astronomical observations. To identify these complex substances, scientists use a variety of methods, each based on different ways in which molecules interact with light. One key technique is spectroscopy, a powerful tool that analyzes the light emitted or absorbed by materials in space. When light passes through or interacts with a cloud of gas or dust containing molecules, certain wavelengths of light are absorbed at specific frequencies, creating unique patterns known as absorption or emission lines. By looking closely at these spectral fingerprints, astronomers can determine what molecules are present there. For example, water, carbon dioxide, and various organic compounds have unique signatures that indicate their presence in different environments, such as interstellar clouds, planets, or the atmospheres of distant exoplanets. Another way is to use radio telescopes to detect molecular emission in the radio band. Many complex molecules emit radio signals when they change from one electronic state to another. By observing these emission lines, the physical and chemical properties of celestial bodies can be understood, allowing scientists to determine the types and amounts of molecules present. One example is the discovery of methanol, which is often found in interstellar regions. Space missions and telescopes equipped with specialized instruments such as the Atacama Large Millimeter Array, the Submillimeter Array, and the James Webb Space Telescope have greatly improved our ability to see complex molecules. These observations not only focus on well-known molecules, but we are also investigating the presence of new and exotic compounds that contribute to our understanding of space chemistry. With these techniques, we continue to unlock the secrets of the universe, revealing the complex tapestry of molecules that may eventually lead to the origin of life. Interstellar space is rich with an amazing variety of complex molecules, some of which are quite intricate and important for understanding space chemistry. Among the most visible are a class of organic compounds known as polycyclic aromatic hydrocarbons. These molecules, consisting of several fused benzene rings, are thought to be formed in high-energy environments such as stellar processes. Their presence indicates the complexity of chemical reactions in space and suggests that the building blocks of life may be larger than previously thought. Another exciting discovery is amino acids, the building blocks of proteins. Certain amino acids have been found in meteorites and in clouds of gas and dust throughout the galaxy. For example, glycine, the simplest amino acid, was discovered in a cloud of atoms called Sagittarius B2. The existence of such compounds supports the idea that the raw materials for life may have spread throughout the universe, possibly leading to the development of life as we know it. Glucose and alcohol have also been found in interstellar regions. Complex sugars such as ribose, an important component of RNA, have been found in samples of comets and gas clouds. In addition, molecules such as ethyl alcohol have been discovered, demonstrating the variation of carbon in space. These discoveries not only expand our understanding of the molecular complexity of the universe, but also point to ways in which these materials can shape life. These complex molecules show that the universe is full of matter, and form a bridge between the phenomena of the universe and the processes that give rise to life. As scientists continue to explore the vastness of space, they are discovering complex connections between elements formed in stars and organic compounds that may one day explain the origin of life on Earth and beyond. The formation of the organic molecules necessary for life in the universe is a fascinating process that begins with the simplest elements that arose shortly after the Big Bang. As the universe cooled, matter began to condense, and primordial hydrogen and helium provided the basis for more complex structures. Over time, the gravitational attraction of incoming particles led to the formation of stars, which played a crucial role in creating the diverse set of elements we see today. At the heart of stars, nuclear fusion occurs, turning hydrogen into helium, and heavier elements such as carbon, nitrogen, and oxygen are formed by subsequent fusion processes. When stars exhaust their nuclear fuel, they release these elements into the surrounding interstellar medium through powerful supernova explosions or stellar winds. Enriched cosmic dust and gas provide a fertile environment for the synthesis of organic molecules. In colder and denser molecular clouds, simple molecules such as carbon dioxide, ammonia, and water can combine to form more complex organic compounds. These reactions often occur on the surface of interstellar dust grains, promoting interactions that lead to the creation of molecules such as amino acids, nucleobases, and sugars. The ability of these dust grains to act as a catalyst is a key factor in the development of the rich chemical composition necessary for life. In addition, the dynamics of chemical processes are influenced by cosmic rays and ultraviolet radiation, which can provide the energy needed for reactions to occur. As comets and asteroids form and transport these organic molecules through space, they may eventually collide with planets. This transport mechanism offers intriguing prospects for how the basic ingredients for life can be delivered to Earth-like planets, and possibly trigger the chemical processes that have led to the emergence of living organisms in various environments throughout the universe. Polycyclic aromatic hydrocarbons, often abbreviated as PAHs, play an important role in our understanding of space chemistry and the possibility of life beyond Earth. These complex organic molecules are composed of many cross-linked benzene rings and are a rich component of interstellar space. Their formation processes and their ubiquitous presence provide valuable clues about the chemical evolution of the universe. One of the main significance of PAHs is their connection to star formation and the interstellar medium. These molecules may serve as reservoirs for carbon, which is a crucial element in the formation of more complex organic compounds. Their detection in dense molecular clouds suggests that PAHs are part of ongoing processes that contribute to the chemical richness of the universe. Moreover, as stars form from these clouds, PAHs may play a role in radiative processes that affect the environment surrounding the new stars, influencing the formation of additional molecules. PAHs are also close to the question of the origin of life. The structure of PAHs shows that they can participate in a variety of chemical reactions, leading to the formation of important biological molecules. Some studies suggest that PAHs may be precursors to amino acids and other macromolecules necessary for life. Life in the remnants of old stars and galaxies offers interesting possibilities for the evolution of complex matter into living molecules. In addition, the discovery of PAHs in the atmospheres of distant exoplanets will expand our understanding of chemical processes beyond the solar system. Their discovery may be a sign of carbon chemistry occurring in other worlds and raises important questions about how this environment can survive. Polycyclic aromatic hydrocarbons are not a common indicator of atmospheric activity. This may be the interface between the simple and complex matter necessary for life as we know it. Molecular clouds are dense regions of air and dust in space, containing mostly hydrogen, but also many other elements and compounds. These clouds are important for the chemical evolution of the universe because they serve as the first site of formation and interaction of complex molecules. The abundance of material in molecular clouds creates the necessary environment for numerous chemical reactions to take place, laying the groundwork for the emergence of stars, planets, and perhaps life itself. When stars begin to form from the gravitational collapse of part of a molecular cloud, they trigger a cascade of chemical and physical processes. The intense heat and pressure inside the new stars leads to nuclear fusion, which produces heavier elements that enrich the environment. When stars reach the final stages of their life cycle, they explode as supernovae, scattering newly formed elements such as carbon, oxygen, and nitrogen back into space. This material then mixes with existing molecular clouds, improving their composition and promoting the formation of even more complex molecules. The interactions that occur in molecular clouds are very interesting because they allow for the synthesis of different types of carbon atoms. The reactions taking place in the dust particles act as catalysts, allowing simple molecules to combine to form more complex structures. For example, amino acids, sugars, and other organic compounds have been found in these clouds. The presence of these complex molecules indicates that the building blocks of life exist in the universe. Molecular clouds are not only important for the formation of stars and the chemical building blocks necessary for life, but also contribute to global change. As stars are born and die, they contribute to the changing chemical landscape of galaxies. This continuous process creates a complex chemical network that connects different parts of the interstellar system and forms the structure of generations of stars and planetary systems. Thus, molecular clouds are an important part of the chemical history of the universe. Every night, astronomers scan the sky for possible habitable worlds and extraterrestrial radio signals. So far, no signs of life have been detected. But are all these searches in vain? Are we alone? This is a very important question because the answer has a lot to do with our place in this vast expanse of space. There is one hypothesis, called the unique Earth hypothesis, that says we shouldn't look for life in other stars. But is this hypothesis correct? We'll start with the broader concepts, then focus on the hypothesis itself, and then look at recent discoveries to see if they fit. Here is our proposed plan. We haven't talked about this kind of theory on our channel yet. We cover a lot of different topics, so what comes next will be particularly interesting. You've probably heard the term habitable zone around a star. Well, the place where exoplanets are at a suitable distance for the origin of life, where it's not too hot but not too cold either, is also called the Goldilocks zone. But did you know that a galaxy also has its own habitable zone? And not all galaxies are habitable. The further a star is from the galactic nucleus, the lower its metallicity, i.e., the lower the amount of elements heavier than helium. This decrease is due to the formation of heavy elements in the cores of giant stars and supernovae. Such stars are concentrated in much higher concentrations near the galactic core because there is enough material there for them to form, which means that the most distant stars in the galaxy lack the ingredients for life. A supermassive black hole is usually at the center of a galaxy. It can emit huge amounts of X-rays and gamma rays. All nearby exoplanets are constantly exposed to this deadly radiation. Life could never thrive in such conditions. Our galaxy is of the spiral type, with dense arms extending to the edges. Such arms also become destructive to life. Here, stars regularly pass close to each other and disrupt the orbits of exoplanets. Imagine if Earth suddenly entered Mercury's orbit. In addition, these regions also have the problem of nearby supernovae. As supermassive black holes, They regularly emit deadly radiation. NJA indicates that the habitable zone of Xalax is a place close enough to the center of the galaxy with enough complex elements, but far enough away from the core and arms to avoid gravitational disturbances and radiation overdose. We are still in the early stages of understanding what part of the galaxy is habitable. For the Milky Way, all of these factors would make most stars unsuitable for life. The remaining stars must be of the right type and planetary structure for life. We used to think that every star had a habitable zone, the theoretical distance at which liquid water could exist. However, this is a very simplistic viewpoint that does not take into account the spectrum or habitability of stars. For example, low-mass stars emit much less visible and infrared light than main-sequence stars, but they can emit huge amounts of X-rays and gamma rays. This means that their habitable zone may contain water, but the levels of X-ray and gamma rays are so high that the complex molecules might just break apart, killing any possibility of life. The deviation of light from our Sun is very small, less than 0.1%, but for other stars, it can vary by up to 500%. As a result, the boundaries of the habitable zone move throughout the system as stars get darker and brighter. This means that worlds become habitable and escape, which in turn kills all possible life. But even if we find the right stars, it's not at all certain that the planet will be suitable for life. We also need the planets to be properly aligned. The configuration of our system is as follows. Rocky planets are close to the star, while gas giants are farther away. Rare in other star systems. Most only have rocky worlds or gas giants near stars known as hot Jupiters. But in our case, it was this unique setup that helped give birth to life. There is a direct correlation between the number of planets in a star system and their circular orbits. Systems with only 1 or 2 exoplanets tend to have highly elliptical orbits, meaning that an exoplanet can go in and out of the star's habitable zone during the course of a year, again destroying life. However, systems with increasingly large exoplanets have orbital resonances. This creates much more circular and stable orbits, so an exoplanet can remain in the habitable zone all year round. Orbital resonance is too complicated, but the point is that such a system is balanced and keeps each planet where it should be. And as the Earth begins to approach the Sun, orbital resonances pull it back, and vice versa. But even if we get orbital resonances, rocky inner worlds, and outer gaseous exoplanets, the likelihood of finding life there is slim. Models of the early solar system show that Jupiter was crucial to the origin and development of life on our planet. Jupiter has orbital resonance with every asteroid in the asteroid belt, keeping them between itself and Mars. Because of this effect, asteroids will constantly bombard the Earth, and life cannot thrive. Why, if there were no Jupiter, life would be unlikely to have started. At the dawn of the solar system, it actually drifted into the interior of the solar system and threatened to destroy the inner planets. But Jupiter has a unique resonance with Saturn, and Saturn with Uranus, and so on. This resonance meant that Saturn pulled Jupiter out of its inner spiral, preventing a collision with Earth and Mars. Consequently, for life to arise on an exoplanet like Earth, we need, among other things, a unique planetary arrangement. But that's not enough. It also requires the right type of planet and satellites to become habitable. First, the size of the planet requires the right gravity, or it can be very unfriendly. If there is too much light, the atmosphere and liquid water can simply escape into space. This is exactly what happened with Mars. Also, the planet's atmosphere must have the right composition, or it will be uninhabitable, like Venus. Its atmosphere has a high concentration of carbon dioxide, making it the hottest planet in the solar system, even though it is in the habitable zone. The geologic forces created by plate tectonics, mountains, volcanoes, earthquakes, and deep-sea trenches are crucial for life. First, We believe that life had to have originated around hydrothermal vents caused by tectonics, so it could not have existed without them. And secondly, tectonics is very important for complex life, but more on that later. Tectonics occurs when molten rock mixes with the Earth's core. This iron-rich magma rises to the surface and helps create Earth's magnetic field. The field that protects the planet from the solar wind and is an important shield not only for organisms but also for the atmosphere. Without a magnetic field, as we know, the Earth would quickly become uninhabitable. Our tectonics is aided by the radioactive decay of the planet's core, internal heat, and suddenly, the moon. Our month is unusual. It is by far the largest moon for its planetary size, with a mass of 27% of Earth's mass. This means that its gravitational pull on the Earth is enormous. This creates tidal friction and heats the planet's mantle. And without a massive moon, we may not have vital tectonics. But the moon does something else. It stabilizes its axial tilt. The Earth, as we know it, rotates at a slight tilt, which is why we have seasons. The moon's tidal forces keep its tilt constant and stable. You can see how many shades there are. Suppose we found an exoplanet with the right planetary structure, the right size, the right composition, plate tectonics, and a large exoluna around the right stars in the habitable zone of the galaxy. Will there be life? Probably, yes, we do. Scientists are currently studying Mars to see if life existed on it billions of years ago when it had oceans, plate tectonics, and a dense atmosphere. If evidence is found, there is almost certainly life on these distant worlds. But it's important to realize, not complex life, but simple life. More than bacteria. Complex life, such as multicellular or intelligent life, requires special conditions. In fact, life has existed on Earth for at least 3.5 billion years, but truly complex multicellular life first appeared only 540 million years ago. For 3 billion years, only the simplest organisms lived on Earth. Little by little, much more complex structures began to evolve. But it is still very far from animals and plants now. These early multicellular organisms resembled an amoeba and consisted only of mountain cells. But you know what's amazing? This cooperation of cells seems a complete coincidence. The probability of this event happening again is negligible, as it took 800 million years. There is a high probability that multicellular life is pure chance. But that's still not hard life. It took a natural revolution to create our complex ecosystems. It happened about 541 million years ago in the Cambrian explosion. Imagine that the Ice Age has just ended. The Earth is gradually warming. Glaciers are flowing down from mountainous regions, releasing massive amounts of nutrients into the oceans. Algal blooms are in full bloom, and the atmosphere is filled with oxygen. Those nutrient-rich mountain ranges only came about because of tectonics, so the Cambrian explosion could not have happened without it. Thus, tectonics seems crucial to complex life. The abundance of nutrients and oxygen meant that organisms could afford to burn energy and move elsewhere to feed. Some then evolved to prey on other species. In a few million years, life evolved from very simple sponge vacuoles to crustaceans, squids, vertebrates, and sea stars. We talk about life all the time, but understand, we can't call these Cambrian creatures intelligent. Do you know what I mean? To summarize, what does a planet need for life to exist? A planet has to be in a habitable part of the galaxy, have the right type of star, the right type of orbit, the right type of planetary neighbors, the right size, the right composition, the right tectonics, a large moon, and a natural disaster that results in multicellular life. There are so many factors. It turns out that Earth is incredibly unique, and the odds of finding a duplicate are vanishingly small. Or maybe we're looking at it wrong. In recent years, this hypothesis has run into a out-of-nowhere kind of problem. Some satellites of Jupiter and Saturn have liquid water beneath the surface and probably have hydrothermal vents. Here's how they can hide life. This has led some scientists to question the unique Earth hypothesis. If we detect life on distant ocean moons, it should be so simple that this hypothesis will have to be rejected because we have a new model for colonizing a planet, or rather, a satellite. In addition, there are many Jupiter-type planets in the galaxy. And since both of our gas giants, Jupiter and Saturn, have oceanic satellites, I'm referring mainly to Enceladus and Europa, we can expect that there are many fully habitable exolunes. We may never find a twin Earth, but there seems to be a strong possibility that somewhere in space we may find worlds and other life even more alien than our own. It is no secret that at the center of the Earth is a very hot core. Did you know that it is getting colder slowly but surely? What happens when that happens? Simply put, it's becoming. And to be a little more specific, the planet's rotation is slowing down, which is significantly reshaping the Earth's crust. But that's not a bad thing. Convection currents in the mantle disappear, which means the planetary dynamo disappears. The Earth loses its magnetic field and becomes completely defenseless against cosmic radiation that destroys all life on the surface. This bleak picture ends with the solar wind blowing smoothly from Earth into the atmosphere and changing the view of our planet Mars. All in all, the outlook is not bright. But our goal is not to scare you about the end of the world. We're talking about something else. We talk about the interior of our Earth because few people know that it also has an outer core and is in a liquid state. How do we know this? After watching this video, you are probably even more afraid of earthquakes. Anyway, as always, it's going to be interesting. So for now, let's head out into space to look at our home planet. Looking at this insanely beautiful little ball, we see that it is about 70% covered in water. There's no secret. In fact, all oceans are simply floating on top of giant layers of argillite that mankind once decided to call land for some reason. In fact, the concept of buoyancy, where lower density objects rise above higher density objects and the latter sink accordingly, can explain processes on a much larger scale than the existence of oceans. Similarly, we can explain why ice, a solid, can float on top of liquid water, why helium-filled balloons float in the atmosphere, and why rocks sink when we throw them in a pond. The latter simply requires a different way of looking at things. Rocks don't sink, and the water, which is less dense, rises around the rock, and this same principle of buoyancy explains the layered structure of our planet. In fact, the rarefied atmosphere of all layers of our planet's crust floats only on the liquid ocean, which in turn crawls over the crust, moving through the even denser mantle. The mantle is ultimately unable to descend to its lowest and densest point, the core. Ideally, the most stable state the Earth could be in would be layered like an onion. The densest elements would be closer to the center, and each outer layer would consist of progressively less dense elements. In fact, each earthquake is a sign that the planet has come one step closer to its ideal, because after each earthquake, the speed of its rotation, although insignificant, but still increases. This is exactly how our world, and other planets as well, are organized. All that remains is to remember where all these elements come from. Long ago, there was almost nothing in the universe except hydrogen and helium. The heavier elements were created by the stars and returned to the universe after their deaths to form the next generation of celestial bodies. But for Saros, a whole cocktail of new elements was born. Nitrogen, silicon, magnesium, carbon, oxygen, sulfur, and iron were added. And around almost all of them, new stars and protoplanetary disks begin to form. The external pressure of a newly forming star basically pushed the lighter elements to the outer parts of the future star system, and gravity caused its unstable disk to collapse and soon to form planets. Speaking of the solar system, The four densest planets by far are in its interior. All of them could not gravitationally hold the large amounts of hydrogen and helium from which they were formed, so they did not become gas giants. But the outer planets, which were more massive and farther away from the Sun and therefore received less radiation, were able to retain large amounts of these ultralight elements and form gas giants. Earth and other worlds are similar in structure. The densest elements concentrate in the core, while the lighter elements form the less dense layers surrounding them. Not surprisingly, the heaviest and most stable element in the Earth's core, iron, has become the most abundant element, and huge masses of it are formed by supernovae. But not everyone knows that between the solid core and the mantle is a 2,000-kilometer-long layer of liquid called the outer core. Our planet has a liquid layer that makes up 30% of its total mass. We have only been told about this by scary soothsayers, seismic waves caused by earthquakes. There are two types of seismic waves during an earthquake. A pi wave, also known as a primary pressure wave, is a type of pulse on a stressed surface. The E wave, also known as the secondary transverse wave. Its journey is like the movement of a wave across the surface of the sea. Both waves travel outward from the point of origin, spreading their vibratory effects not only over the surface near their epicenter, but also around the world. Therefore, seismic monitoring stations analyze both types of waves. However, S waves do not propagate through a fluid, unlike P waves, which not only can travel straight through a fluid, but can also be refracted. As a result, we know that the Earth has a liquid outer core, a solid mantle on the outside, and a solid core on the inside. This is why the heaviest and densest elements are in the core of the planet. But why is the outer core in a liquid state? All the elements we know, and with them iron, are the same in many forms, depending not only on pressure but also on temperature. The problem is that iron is much more complex than most of the elements we know. It is capable of various crystalline solid forms, but today we are not at all interested in talking about normal pressure. No, we're going to the Earth's core, where the pressure is hundreds of times higher than water pressure and millions of times higher than atmospheric pressure. But first, it's important to realize that the atmosphere has a density of about 0.001 gigapascals, and the inner core has a density of about 330-360 gigapascals. 330 gigapascals requires simply amazing temperatures comparable to the surface temperature of the Sun, which, I remind you, makes it possible to melt iron. However, at the same temperatures but lower pressure, iron easily remains liquid and solidifies as the pressure increases. How does it threaten the Earth's core? The highest temperature at the center of the Earth is just below 6,000 Kelvin, the same level at which the melting point of iron at the boundary between the inner and outer core is also at, according to recent estimates. Our dear Earth is gradually cooling down. It radiates heat into space faster than it produces heat itself through radioactive decay. Inside the Earth, the internal temperature drops, but the pressure remains constant. In other words, our home planet was still this warm creature waiting to be born. Its temperature was much higher than it is now. Perhaps the entire core was once liquid, and now that it is cooling, the inner core continues to grow. The final stage is complete cooling and the formation of a giant lump of iron inside our planet. The density of solid iron and its sheer mass causes our planet to shrink, which is why we get just a huge number of earthquakes. To summarize, the fluidity of the core is due to its temperature, which allows the iron to melt, though only where the pressure is reduced. And the Earth is getting older and colder. More and more areas of the core solidify, and because of this, our beautiful planet is constantly shrinking, albeit very slowly. If you want to know what this looks like, take a look at present-day Mercury. Here, you can see the same huge edges of the largest ones. Mercury itself took a long time to cool down and shrank very hard, causing giant cracks of tens or even hundreds of kilometers to appear there. We just need to remember that every earthquake is a wake-up call. That means only one thing. Earth is a little closer to finally cooling and solidifying. If you were offered to visit any part of the solar system, where would you go? Perhaps you would choose the inner part where our rocky planets Mars, Venus, Mercury are located. Or maybe you want to go outside and look at Saturn, Jupiter, or Uranus. Or you can travel beyond the orbit of Neptune to see Pluto and Poscope. We suggest you go to the part of the solar system where Mars's mansions have ended, but Jupiter's dominion has not yet begun. Straight to the asteroid belt. This mysterious place contains many marvelous objects that can tell us a lot of interesting things. This is where NASA plans to send its new spacecraft to study one of its inhabitants in detail, asteroid Psycho 16. This subject is special. It's been called the savior of mankind. The asteroid belt is often referred to as the main asteroid belt or simply the main belt, thus emphasizing its difference from other similar areas of small planet clusters, such as the Kuiper belt and the cluster of scattered disk objects, or the Oort cloud. The total mass of the main belt is equal to about 4% of the Moon's mass, with more than half concentrated in the four largest objects: Ceres, Pallida, Vesta, and Hygeia. Ceres is the largest and only dwarf planet in the main belt, measuring more than 950 kilometers in diameter and twice the combined mass of Pallida and Vesta. But most asteroids, of which there are several million, are much smaller, down to a few tens of meters. In addition, asteroids are so widespread in this region of space that they have not harmed any spacecraft passing through the region. In the 19th century, it was widely hypothesized that the asteroid belt represented the remains of the erstwhile planet Phaethon, which was destroyed in a collision with a large object millions of years ago. Then we attended these events and even hosted them. This is a joke, of course, but we actually have this video, and if you haven't seen it, you can watch it. At the same time, you can compare how much our channel has changed in a few years. As for the Phaethon hypothesis itself, it was soon firmly rejected, one of the most important arguments being the total low mass of the belt. But then how did the belt form? The main theory now is that it started forming right near Jupiter, whose gravitational field was constantly introducing serious perturbations to the orbits of planetesimals. The excess orbital energy received from Jupiter caused these bodies to collide more violently with each other, preventing them from being blindsided by the protoplanet and further enlarging it. As a result, most of the planetesimals were fragmented into numerous small fragments, most of which were either ejected outside the solar system, which explains the low density of the asteroid belt, or moved into elongated orbits on which they, getting into the inner region of the solar system, collided with the planets of the Earth group. Collisions between asteroids occurred after this period, which led to the appearance of numerous asteroid families, groups of bodies with similar orbits and chemical composition, which includes a significant number of existing today asteroids, as well as the formation of fine cosmic dust that forms the zodiacal light. In addition to this, Jupiter's gravity also creates regions of unstable orbits where asteroids are virtually absent due to resonances with Jupiter. An asteroid getting there in a relatively short time would be ejected from that orbit outside the solar system, or would join the population of asteroids crossing the orbits of the inner planets. Now, there are almost no asteroids in such areas, but the orbits of many small asteroids continue to slowly change under the influence of other factors. There is also a version that the asteroid belt was formed as a set of byproducts in the formation of the planets of the solar system. In other words, asteroids formed as debris from the formation of other planets, which were then dropped into the region between Mars and Jupiter, where they are today. The most important distinguishing feature of individual asteroids is their spectrum, by which we can judge the chemical composition of a particular body. There are three main spectral classes of asteroids in the main belt. Attention on the screen: carbon, silicate, and metal, or iron. All of these classes of asteroids, especially metallic asteroids, are interesting from the point of view of the space industry and especially industrial asteroid exploration. Asteroid Psyche 16 belongs to the iron class. Its shape is similar to a potato, only it is very large, with a diameter of about 226 kilometers and dimensions of 2 to 79 x 232 x 189 kilometers. Psyche orbits the Sun at a distance of 2.53.3 astronomical units. Recall that 1 astronomical unit is the distance between the Earth and the Sun. Psyche takes about 5 Earth years to make 1 revolution around a star, and it takes just over 4 hours to make 1 revolution around its axis. Today is Psyche's day, mostly made up of 90% iron, nickel, and other metals, very similar to the core of a planet. It has even been suggested that Psyche is the high metal core of an ancient protoplanet that may have been destroyed by collisions with other asteroids before it could complete the process of becoming a full-fledged planet. An interesting asteroid is the primary target of the Psyche mission. According to already announced plans, the U.S. Space Agency will send its equipment there in 2022. The main goal of the mission is to find out if Psyche is indeed the core of a planet-sized object and to learn more about the formation of the solar system. But is that the main goal? Or maybe NASA is being a little silly? The fact is that in the media there was information that simply stirred up the public. They report that in addition to nickel and iron, the psychic rocks also contain platinum and gold. Some experts have even calculated the total cost and came up with an impressive sum of $700 quintillion. And according to the space treaty drawn up by the United Nations, space is not a matter of national property, but belongs to all of humanity. It turns out that this money is enough to eradicate poverty on Earth forever, because each of us is entitled to about $2 billion. It became a harsh name like savior of mankind. But before you start planning what to spend your rightful $2 billion on, I'm going to quickly disappoint you. There is no gold and platinum for the Psyche, even in such quantities. It's a complete fabrication. But so popular that even NASA had to step in to assuage the gullible minds of the dubious article. The organization officially denied any suggestion of gold reserves, stating that Psyche 16 is not made up of gold, but iron and nickel. NASA also claimed that even if Psyche 16 was full of gold, the cost of mining would be too high and therefore the profit would be zero. But of course, this NASA claim can be refuted. They say they are deliberately not hiding the duty to destroy everything under them. But let's think about this. No satellite spectrometer can detect gold. It can only be determined by some circumstantial evidence. Furthermore, it is not known exactly how gold is normally formed today. Just theories. How is it suddenly known that the Psyche has reserves and so many? It is believed that gold is formed during the explosion or collapse of a supernova due to the collapse of neutron stars. According to this theory, after an explosion, metal and metal-containing dust, including heavy metals such as gold, are ejected into space where they later condense. That's exactly what happened in the solar system. And since the Earth was in a molten state right after birth, almost all the gold on Earth is in the core. The logic here is probably this. Since Psyche is thought to be the core of an amorphous planet, this means that it, like Earth, is full of gold. That's about it. Of course, our solar system is rich in mineral resources, and there are indeed many resources that can be turned into money. The entire space market is already worth hundreds of billions. More and more people are talking about it, including us here on the channel. We made a video about it. And it is inevitable that development of these resources will begin in the near future. And while some companies believe that asteroid mining is the most promising industry in space, such as NASA's Psyche asteroid mission, in reality, it is probably purely scientific in nature and aimed at studying the formation of the solar system.
There are a lot of really scary places in our universe, and most of them are cold worlds where life could never arise. But even among all this dark variety, there are objects that we can call the most dangerous exoplanets we've discovered. And now I propose we go to the most incredible one of all. In 2020, just before Halloween, NASA compiled a list of the scariest worlds, including 6 exoplanets. Each one is an object that not only has extreme conditions for any living organism, but even being near it can be fatal. The first of these was a gas giant called TRES 2b. This celestial body orbits the star TRES 2, a yellow dwarf located 718 light-years away from us. TRES 2b has a unique surface chemistry that allows the planet to absorb more than 99% of the light falling on it. The reason for these features is not yet known, and there may be chemical reactions going on in this celestial body that we have not been able to detect with any similar object before, and they are what make TRS 2b the darkest exoplanet we know. This gas giant was discovered on August 21st, 2006, and more detailed characteristics were obtained a few years later. TRES 2b has a mass of 1.2 Jupiter masses and a radius of 1.27 Jupiter radii. The planet's atmosphere is heated to 1,000 degrees Celsius, causing the exoplanet to emit a faint red glow that looks like glowing coal. Despite all its gloomy appearance, TRS-2b cannot be called the most dangerous place in our universe. In addition, there are many more scary objects hidden in space. It is an exoplanet called 55 Cancri 1, located in the system of the Sun-like star 55 Cancri He. This celestial body was discovered on August 30th, 2004, using Doppler spectroscopy. This planet has a mass approximately equal to 8 Earth masses and a radius of 1875 Earth masses. 55 Cancer 1 is in an ascending lock, so it never dawns on one side of the planet and never gets dark on the other. Therefore, the side facing the star is always heated to plus 2,400 degrees Celsius, while the temperature of the night side is plus 1,300 degrees Celsius. Such a large number can be explained by the fact that the planet's distance from the star is only 183 tens of thousands of astronomical units. In addition, the planet likely has volcanism, which regularly ejects dust clouds that prevent heat production. A day on this planet lasts just under 18 hours, and the atmosphere contains helium and hydrogen. It also contains a high proportion of carbon, which likely forms thick layers of graphite and diamond in the planet's interior. However, 55 Cancer 1 is not the only object in the planetary system of its star, because in addition to it, there are 4 other celestial bodies. All of them have much more favorable conditions, and it is this fact that distinguishes the 55 Cancer home system from the next item. This is called Poltergeist, or PSR 1257 plus 12c, and it's an exoplanet located in the pulsar system. This object is only 0.36 AU from the center of the system, and it shows that Poltergeist could not have survived the supernova explosion that probably preceded the pulsar. Thus, the exoplanet could have formed after this event, for example, from amorphous material formed after the explosion. There is another hypothesis, according to which a pulsar can be formed by the merger of 2 white dwarfs. And this process is not often accompanied by a loud explosion. But since this is the first time we have observed such objects, science still doesn't know the exact answer to their origin. The celestial body system is located 2,300 light-years away from Earth, and by mass, Poltergeist is about 4 times more massive than our planet. It has a rotation period of about 66 days. In addition, if we ever get close to this mysterious object, the radiation streams emitted by the pulsar would likely destroy all spacecraft. Given all these features, Poltergeist cannot be called the most dangerous exoplanet we know. In fact, if a small space body, when approaching it, can simply collapse, then in close contact with the next object, it will completely vaporize. The reason for this is the extremely high temperature of Kepler 70b, the hottest exoplanet known to us. This object orbits the dwarf star Kepler-70. The surface temperature here is higher than our Sun and is 6,800 degrees Celsius. The object has a mass of 0.44 Earth masses and a radius of 0.76 Earth masses. The rotation period of this celestial body is 345 minutes, so the day here lasts less than 6 hours. At the same time, the exoplanet regularly passes by another object of the system, Kepler-70c, at a distance of 240,000 kilometers, and it is now the closest planetary transit we have been able to record. The extremely high temperature of this celestial body can be explained by the fact that this object may have once been part of its parent object. However, the final recognition of Kepler-70b exoplanet is currently an open question. It is worth noting that Kepler-70b is not the only celestial body known to us, so closely interacting with its parent star. Another object in similar circumstances is an exoplanet called WASP-12b, or WASP-12b. This celestial body is 870 light-years away from our system. Its radius is 1.93 times larger than Jupiter, and its mass is 1.46 times the mass of the solar system's largest planet. WASP-12b is 0.03 AU away from its star. Because of this close coexistence, the temperature of WASP-12b reaches 2200 degrees Celsius. And due to the extremely strong gravity of the parent star, the star will gradually absorb this celestial body, and in about 10 million years, the exoplanet is likely to completely disintegrate. Given all these circumstances, it is unlikely that we will be able to delve deeper into the study of this planet. Such worlds do not seem to be of primary interest to science. However, some of them have truly unique properties, and despite their appearance, harbor much more danger than meets the eye. For example, when you fly past HD 189733b, you might think it's a safe planet because it looks a lot like our Earth. But as they descend into its atmosphere, each passenger faces several deadly dangers. The winds here are made up of silicate particles and have a speed of 8,700 kilometers per hour. In addition, the exoplanet is experiencing rains that cause precipitation of molten glass to fall on the surface. The main reason for such deadly weather is the extremely high temperature and composition of the atmosphere. An exoplanet's orbital period around a star is about 2.5 days, and most likely, the planet is always facing the star in the other direction. In terms of its properties, HD 189733b is a light blue gas giant in the constellation of Foxy. Its distance from our system is only 63 light-years, and the diameter of this object is 1/10 of the diameter of Jupiter. The mass of the exoplanet is 13% more than the mass of the largest planet in our system, orbiting the orange dwarf. The distance between HD 189733b and its star is 30 times smaller than the distance between Earth and the Sun, and is about 5 million kilometers. Due to this proximity, the exoplanet maintains a constant temperature of about 930 degrees on the bright side and does not drop below 425 degrees on the dark side. The first studies of this object began immediately after its discovery. And in 2007, using Hubble data, scientists discovered that HD 189733b has a hazy atmosphere. Also, when the planet is between an observer on Earth and the star, its atmosphere takes on a reddish hue. The possible cause of this effect is atmospheric fog, which, according to preliminary estimates, consists of iron particles, silicates, and aluminum oxide. In addition, scientists were able to confirm the presence of water vapor, neutral oxygen, and the organic compound methane in the planet's atmosphere using Hubble data. And after a second study, the presence of carbon monoxide on the day side was confirmed. However, the greatest number of questions caused the research, according to which in the atmosphere of the planet were found traces of methane, which is in a special fluorescent state, emitting electromagnetic radiation in the EC range. This state of matter suggests the presence of unknown activity in the atmosphere of HD 189733b, which has yet to be unraveled. Thus, thanks to the study of this object, we can conclude that even on the most uninhabitable exoplanets can still occur processes that are of interest to science. And while the process of their research will continue, such worlds will long remain only horror planets for us and always remind us of how lucky we are to have our Earth. The universe is full of countless other worlds. Of the thousands of exoplanets discovered beyond our solar system, none could be considered more hospitable to us than Earth. Some are melting from the unbearable heat of nearby stars. Others are forever encased in ice or burned by destructive radiation. But among the many unfriendly worlds, there are some very different ones. On their surface, oceans swirl and rivers flow, clouds float across the sky, and the atmosphere is full of torrential rain and thunder. Perhaps these worlds could become the cradle of beautiful and unique life as Earth once was. And today, we'll move on to the most important of them all, space. It can hardly be denied that life is one of the most marvelous, complex, and mysterious phenomena in the universe. Although we have studied it for millennia, many important questions about it remain unanswered. And most importantly, how widespread is biological life beyond our planet? At present, it is impossible to say with certainty whether the Earth's biosphere is a unique phenomenon or whether it arose as a natural result of long evolution. It is not surprising that the search for life beyond Earth is one of the most important scientific directions. And in this regard, the so-called Earth Similarity Index, or ESI, was developed to identify the most promising celestial bodies. It's based on two basic parameters. This is the level of gravity on the surface of a celestial body and its equilibrium temperature. According to researchers, these parameters determine how much another world can be similar to the Earth and how favorable the conditions on its surface are for hypothetical life. The undeniable advantage of the ESI is its simplicity. When an exoplanet is discovered, you can usually determine its approximate orbit, mass, and size, and this information is only enough to calculate the basic parameters of the index. However, while attractive, it does not take into account many factors important for sustaining life. We are therefore developing our ESI-based evaluation system and augmenting it with several important parameters. One of them is the action of the parent star. It is known that the recurring eruptions and stellar matter emissions characteristic of red dwarfs can negatively affect the atmospheric stability and radiation background of nearby exoplanets. However, red dwarfs are considered more favorable than large stars such as Sirius or Vega because the life of giant stars is too short and the radiation is too destructive, leaving room for the possible development of life. Orange and yellow dwarfs, including our Sun, are considered the most beautiful. Another important factor can be considered the probability of tidal locking, which depends on the distance between the exoplanet and the star. Celestial bodies that are too close to the star are constantly rotating in the other direction. Therefore, there is a large temperature difference between their day and night sides. Too great a distance from a source of heat and light takes a planet out of the habitable zone, drastically reducing its habitability. It is also necessary to consider the type and chemical composition of the exoplanet. After all, the development of hypothetical life requires a certain set of chemical elements combined with a characteristic topography. Stony Earth-type planets, or super-Earths, can provide similar conditions, while mini-Neptunes lack solid surfaces, and ocean planets are deficient in many elements. Thus, the set of parameters we have collected allows us to comprehensively assess how favorable the conditions on the selected exoplanet are for hypothetical life. For example, the Earth on such a scheme will look extremely attractive, being a natural benchmark for other objects. At the same time, Mars, although it has the highest index of similarity to our planet in the entire solar system, has a number of obvious disadvantages. It is too cold and has a low mass, and also has a serious shortage of water. Despite appearances, Venus is too hot due to a strong greenhouse effect. And although most of its parameters are in the green zone, the extremely high temperature is a critical disadvantage of the planet, negating all its advantages. So there are not enough Earth-type planets in the solar system to be considered suitable for life. However, beyond its borders, in the vicinity of distant stars, already discovered worlds more than 5,000 years old, some of which in many ways can be considered similar to ours. One of the closest such objects is an exoplanet known as Gliese 1002b. Located just 15.2 light-years away from our planet, it was discovered in 2022 using the radial velocity method. This method is effective for finding relatively close exoplanets by recording the subtle oscillations of the parent star caused by the motion of space objects around it. The exoplanet is located near a small, dim red dwarf known as Gliese 1002. Its radius is only 14% of the Sun's, and its mass is 8 times smaller than that of our star. Given that Gliese 1002's surface temperature is only 3,000 Kelvin, or about 2,730 degrees Celsius, it's not surprising that its luminosity is extremely low, about 700 times less than the Sun's. Observations also show that the object is characterized by a very quiet character, uncommon for stars of this class. Due to the low brightness of this red dwarf, its habitable zone has an extremely small radius and width. However, the object Gliese 1002b is located near its outer edge and can be considered potentially habitable. According to observations, this celestial body makes a complete revolution around the center of the system for about 10 Earth days, from which it follows that the average radius of its orbit is very small and is about 0.46 astronomical units. It is hypothesized that because of its extreme proximity to the parent luminary, the exoplanet is likely in a tidal grip and is permanently turned to one side of it. Calculations show that the celestial body receives from its star 1.5 times less energy than the Earth from the Sun, and the average temperature of its surface can be approximately 230 Kelvin or minus 43 degrees Celsius, which is slightly warmer than Mars. Taking into account tidal capture and a possible greenhouse effect, this means that liquid water could be found on the exoplanet's surface, and thus conditions for sustaining life. At least some terrestrial organisms are able to survive in such conditions. Also, calculations show that the mass of Gliese 1002b is 8% greater than that of our planet, and its radius exceeds Earth's by only 3%. With this information, it is easy to determine the acceleration of gravity on the surface of the celestial body. It's pretty much the same as the value we're used to. So, the combination of all the factors we know suggests that Gliese 1002b is a rocky planet, most of which is covered in ice. It has a fairly high ESI of 0.86 because of its size, close to Earth. In our diagram, this object looks like this. Meanwhile, modeling of the planet's climate shows that its illuminated hemisphere can absorb enough energy to support a liquid ocean with archipelagos, or even full-scale continents. At the same time, tidal deformations coming from the side of the nearest star heat the planet's interior, so the existence of an ocean hidden under the ice, even on its night side, cannot be ruled out. Moreover, Gliese 1002b is not the only planet in the system. At the same time, an object called Gliese 1002c was found to be a little farther away, namely 0.074 AU from the center. This exoplanet has an annual cycle of 21 days, and its mass exceeds that of Earth by about 36%. The object receives 4 times less energy from its parent star than our planet receives from the Sun, so its surface temperature is quite low at about 182 Kelvin or minus 91 degrees Celsius. If we use the previously developed scheme, the exoplanet will look like this. It can be assumed that the conditions on the surface of Gliese 1002c are close to those observed on the satellites of Jupiter or Saturn. Increased volcanic activity caused by the high mass of the planet could be the cause of a hidden ocean with warm and salty water saturated with many chemical compounds. Hypothetically, life could also arise in such conditions, perhaps in highly unusual and unexpected forms. Of course, among the many known exoplanets, there are many warmer and more beautiful worlds. This is, for example, the planet K272e, which is 217 light-years away from us. It orbits a small red dwarf about 4 times the size of our star. Its radius is 0.33 times larger than the Sun, and its temperature is relatively low at 3,360 Kelvin, or about 3,100 degrees Celsius. Observations by the Kepler orbiting telescope have shown that an exoplanet crosses the disk of its parent star every 24 days. This means that the radius of its orbit is very small and is on the order of 0.1 astronomical units, which implies that the celestial body is located within the habitable zone and can be considered potentially viable. The findings also suggest that K272 may be in tidal capture or Mercury-like orbital resonance. Despite the star's low luminosity, the exoplanet receives 11% more energy than Earth receives from the Sun. Assuming K272i's atmosphere is similar to Earth's, the average temperature at its surface should be about 295 Kelvin or 22 degrees Celsius, which is slightly warmer than our planet. It is worth remembering that if the celestial body is in a tidal grip, there is a high probability of extreme temperature differences between the day and night hemispheres. In addition, it is worth considering that its parent luminary, like most other red dwarfs, is characterized by an erratic nature and often demonstrates flares and large emissions of stellar matter, which can have a detrimental effect on the atmosphere and surface of nearby space objects. Meanwhile, calculations show that K272i is 29% larger in diameter than Earth and about 2.2 times more massive than it. Knowing this, we can calculate the level of gravity on the surface of this celestial body. It is about 32% higher than what we are used to. Thus, combining all known data, we can assume that this exoplanet, with a high probability, is a rocky super-Earth, on which liquid water and a dense atmosphere can be found. It has a fairly high similarity index of 0.87, and our diagram shows these objects looking like this. Planets of this type are expected to have a wide variety of chemical elements and a flat topography favorable to life. Undoubtedly, the frequent flares of a nearby star pose a serious threat to the atmosphere. However, a strong magnetic field could hypothetically guide stellar wind particles, and the oceans could protect its inhabitants from harmful radiation. If this is the case, it is conceivable that K272i could display incredible auroras, much more spectacular than those on our planet. As for the hypothetical biosphere that could develop on such a planet, it is likely to be markedly different from Earth's. A different spectrum of incident light may force local plants to use alternative substances for photosynthesis, so their leaves are likely to have a purple or reddish color. In addition, excessive radiation hazards could limit life's landfall or lead to the evolutionary formation of defenses, such as thick skin or specific cellular structures. Similar features are also known in terrestrial organisms, such as the pacifers, archaea, and some fungi. Meanwhile, in addition to this attractive planet in many ways, 3 others have been discovered in the system. 2 of them, called K272b and K272c, are very close to the parent star and slightly larger than our planet. Because of the radiation and stellar wind from a nearby star, they are assumed to be devoid of an atmosphere and similar to Mercury. The third planet, K272d, is estimated to be comparable to Earth, with an orbital radius of approximately 0.08 AU. It makes a complete revolution around the center of the system in about 15 days and is near the inner edge of the habitable zone. Because of its high temperature, the conditions on its surface are likely close to those of Venus, and the likelihood of life forming is very low. Either way, this system is still being explored, which means we have a lot to learn about it in the future. That said, all of the objects we studied were comparable in size to Earth, but for all we know, life can adapt to a wide variety of conditions, including the high gravity that is unavoidable on massive planets. When we move about 1,800 light-years away from the solar system, we can detect a yellow dwarf with parameters very similar to our star. The star, called Kepler 452, is a main sequence star that is only 3.7% more massive and 11% larger than the Sun. In 2015, a very significant exoplanet called Kepler 452b was discovered near this star by a transit method. Using high-precision measurements, we were able to calculate that it is located at a distance of 1.04 AU from the center of the system and makes its annual revolution in 385 days. This position makes the probability of a celestial body being captured by tides very low, which is certainly a favorable factor. Kepler 452b is reportedly about 5 times more massive than our planet and has a radius about 1.5 times larger than Earth's. This means that the gravitational acceleration on the surface of this celestial body is 2.2 times what we are used to. Such a high level of gravity likely helps the planet hold a dense atmosphere and also smooths out its topography, which could be the cause of many shallow and warm seas. It is believed that these are the conditions most favorable for the potential origin of life, but for humans, such a significant attraction would be extremely uncomfortable. It is also known that Kepler 452b receives 10% more energy from its parent star than Earth does from the Sun, and is in its habitable zone. Calculations show that the average surface temperature of the object is about 300 Kelvin, or plus 27 degrees Celsius, which is 11 degrees more than our planet. So the climate of Kepler 452b could be close to what it was in the Mesozoic. However, with a certain composition of the atmosphere, such temperatures can be dangerous and lead to the acceleration of the irreversible greenhouse effect up to the complete evaporation of the oceans. According to some hypotheses, this is the process that radically changed the appearance of Venus several billion years ago. From the combination of all the factors we know, we can assume that Kepler 452b is most likely a rocky super-Earth rich in a wide variety of elements and minerals. It is assumed that because of the increased content of radioactive elements, planets of this type should demonstrate increased volcanic and tectonic activity and high gravity to prevent the emergence of extremely high mountains and deep faults. At the same time, the ratio of land to ocean on the surface of Kepler 452b must be different than on Earth. Consequently, this exoplanet with a high probability can represent a boundless ocean dotted with a scattering of archipelagos. If we take our minds off the dry numbers and try to imagine what life might look like on this amazing planet, so similar to Earth and yet so different from it in many ways, we are faced with a truly fantastic sight. The abundance of shallow, warm seas probably allows us to expect a wide variety of aquatic life forms, from the smallest to the very impressive. As for terrestrial creatures, they are likely to be represented by stocky trees with thick trunks and stocky herbaceous plants. Due to the fact that the spectrum of the parent luminary in this system is close to the solar, the color of photosynthetic parts of local plants is likely to be familiar to us, green or bluish. Various small animals with strong bones and strong muscles can also be seen. Another evolutionary pathway is exoskeletonized creatures, such as terrestrial kinistopods. When it comes to flying creatures, exobiologists are divided. Some believe that high gravity is an insurmountable obstacle to flight. Others believe that the decisive positive factor in this matter is the high density of the atmosphere. In any case, we have several more years of research ahead of us before we can say with certainty that this planet is indeed habitable. Every year, we discover hundreds of new exoplanets. Some are downright rude and even dangerous, others are much like Earth in many ways, but no matter how much we observe other worlds, we still can't reach them.
When we look up at the night sky, we see only a small part of what the universe hides. The part we can see is called the visible universe. And that's really all that our eyes or the most powerful telescopes can see. But imagine for a moment that beyond those twinkling dots of stars, there could be something else, something incomprehensibly great and mysterious. And that's where scientists enter the arena with their most exciting hypotheses about what lies beyond our cosmic horizon. Tonight, we're going to try to explore 5 of the boldest and craziest of them all. Brace yourselves. We are taking a journey beyond the visible to discover the unknown. We're talking about something that sounds like science fiction, but is actually serious scientific research: the Hubble sphere and the possibility of our cosmic twin. The Hubble sphere is the boundary of the universe beyond which objects are moving away from us at speeds faster than the speed of light. It's not that they're traveling faster than light. Rather, it's the space between them and their subjects that is expanding so rapidly. Now imagine that beyond this world, there is another universe with a planet like Earth and inhabited by someone very much like you. The science sounds crazy, but math and physics tell us that anything is possible in an infinite universe. If the universe is truly infinite, there must be duplicates of us out there somewhere. This idea is based on the assumption that if the universe is infinite and contains an infinite number of galaxies, then the combinations of particles that make up our world must repeat somewhere. Which means that somewhere in the vast expanse of space, there is another person watching this video, but perhaps in another universe. Of course, this is just a hypothesis and can't be proven yet. But it does encourage us to consider how big our universe is. Perhaps one day, when science reaches new heights, we will learn more about what lies beyond the Hubble sphere, and perhaps even find our cosmic counterparts. At present, we can only speculate and dream about the infinite possibilities of the cosmos. Now, we're going to talk about the most exciting and perhaps the most fantastic hypothesis: the multiverse hypothesis. Imagine that our universe is just one of countless coexisting universes. These universes could be completely different, with different laws of physics, different initial conditions, or even contain completely different life forms. For example, in one parallel universe, Earth could be a planet where the dinosaurs did not die out, but continued to evolve, becoming the dominant intelligent life form. In another case, the gravitational constant could be so small that stars could not form, and the universe would remain a dark and cold place without light. According to the hypothesis, the multiverse can be divided into different levels. At the first level, there are universes that are just beyond our visible horizon, and in which the same physical laws that apply to us may apply. At the second level, there are universes with different physical constants. The third level represents universes created in the many worlds interpretation of quantum mechanics, where each quantum event creates a new universe. Finally, the fourth level. It contains all mathematically possible universes. One of the most interesting ideas of the multiverse. This suggests that some of them may have a version of us living a completely different life. Perhaps there is someone among you who has become an astronaut and explores distant galaxies. Or you, who never knew what the internet was. And now he's trying to club some wild boar for his evening meal. So, now let's dive into the world of parallel universes, which has recently been beautifully presented in the new TV series Dark Matter. This series, based on the novel of the same name by Blake Crouch, tells the story of a physicist named Jason who finds himself in an alternate version of his life. To get back to his family, he has to go through a series of parallel realities and face an alternate version of himself. This series illustrates one of the most intriguing ideas in physics and philosophy: the possibility of multiple universes, each of which is a reflection of the different paths our reality could take. In each of these universes, the story unfolds differently, depending on choices and coincidences that shape the unique course of events. The theory of parallel universes suggests that for every possible outcome of events in our universe, there is a separate universe in which that outcome occurred. This means that there may exist a universe in which you made another major decision that led to a completely different life. You may have never met your best friend in any of these universes. In the second, you invented something that changed the world. Stephen Hawking, one of the greatest minds of our time, has also contributed to the development of this theory. In his latest work, he proposed a way to solve the cosmic paradox of parallel universes and suggested that some of these universes may be very similar to our own. Dark matter shows how these alternate realities can intersect and interact, giving viewers a unique insight into how events might unfold if the past was different. It makes you think about how fragile and changeable our reality can be, and how small changes can lead to completely different outcomes. So what's going to happen? It turns out that each of us is the center of our own universe, and every choice we make creates a new story. Imagine you are standing at the edge of a vast, vast ocean. You can see the waves reach the horizon, but what lies beyond it? It's the same with the universe. We see stars, galaxies, nebulae, but what lies beyond the cosmic horizon? Maybe there's just nothing out there. This thought may seem strange, for how can nothingness exist? But in cosmology, nothingness necessarily means the total absence of everything. It could be a space without matter, radiation, galaxies, or nothingness in the absolute sense of the word. But even in this vacuum, there can be quantum fluctuations, virtual particles that appear and disappear in the blink of an eye. According to one theory, there may be an infinite void beyond the observable universe. This assumption is based on the fact that the universe is expanding, and with each passing second, the boundary of the observable universe is moving farther and farther away from us. If so, then perhaps there really is nothing beyond our visible horizon. No stars, no galaxies, no light. So when we talk about the possibility that there could be nothing beyond the visible universe, we are not talking about just anything. Let's talk about the limits of our imagination and how far we can look into the abyss of space. The universe is not only what we see, but also what we cannot see, and that every new discovery can completely change our perception of reality. This is why the study of space is a wildly interesting thing that keeps us constantly asking questions and searching for answers, even if those answers may not be to our liking or expectations. The dark flow theory predicts that clusters of galaxies in the universe are moving in a coordinated fashion in the same direction. This is not just random motion, but seems to be caused by some massive structure that is beyond the visible universe. Imagine that our entire cosmic home is drawn to an invisible beacon that we can't see, but can feel through its gravitational influence. This theory came about after analyzing data from the Sunyaev-Zeldovich effect. That allows us to measure the movement of gas in a cluster of galaxies. Scientists have found that these clusters move in a particular direction faster than could be explained by known gravitational forces. One possible explanation for the dark flow is the gravitational influence of objects outside the visible universe. There could be a supercluster of galaxies, or even an entire parallel universe that was connected to ours at the time of the Big Bang. This crazy hypothesis suggests that there may be structures beyond the visible that have a huge effect on everything in visible space. It's as if we've discovered that our universe is just one part of a vast cosmic archipelago where each island affects the motion and fate of the others. The dark current theory has yet to be definitively confirmed, and scientists continue to study its effects to see if it really exists and what might be causing it. If the dark current does exist, it would be one of the most important discoveries ever. Let's talk about what could happen to our universe in the distant future. It's a story about how things might end up freezing rather than hitting. This is a theory known as the Big Freeze. Imagine a universe that continues to expand until no more stars are born and the last ones die out, leaving behind only dim dwarf stars and black holes. The temperature of the universe tends to absolute zero, and everything in it slows to a complete stop. According to this theory, the universe came into existence as a result of the Big Bang, but instead of eventually returning to its original size, it continues to expand forever. Over time, when all the stars have used up their fuel and no new ones are forming, the universe becomes dark and cold. Energy is distributed so evenly that stars and galaxies can no longer form. Interestingly, this process may not just be a slow decline. For example, scientist Christoph Wetterich hypothesizes that the universe was cold and fragile in the beginning, and that over time, key particles became heavier and the gravitational constant decreased. This assumption explains why our current cosmos is dominated by dark energy and why we see density fluctuations in the early universe. So, if the Big Freeze theory is correct, our universe may not be a boiling cauldron of stars and galaxies, but rather an infinite frozen void, like a giant refrigerator. Here, we have come to the end of our space journey to different parts of the universe. Together, we looked at what was visible beyond the boundary and allowed ourselves to dream about what might be lurking in those distant spaces. We've talked about multiverses where any one of us could be anything, and a dark flow that may be pulling us towards something we don't understand. We have considered the idea that there can be nothing absolute beyond the cosmic horizon. We have even allowed ourselves to imagine that our universe is just one of an infinite number of stories unfolding in parallel worlds. Who knows, maybe one day we will be able to confirm these hypotheses or even discover new ones that will overturn our established knowledge. And while we wait for these great discoveries, let's keep asking questions, searching for answers, and enjoying every moment of our marvelous cosmic adventure. After all, curiosity is what makes us human and allows us to dream the impossible. We live in an age of great astronomical discoveries. Thanks to modern orbiting telescopes, we already know more than 5,000 distant worlds. Most of them are really amazing places, unique and mysterious, and sometimes even very dangerous. There are planets illuminated by the light of 2 or 3 lamps at a time, and there are those that are forever hidden in the cosmic darkness. Some of them are terrifying in their extreme conditions, and others are surprising in their unusualness. We've traveled to some of the most terrifying exoplanets in the past. It's time to continue your journey. Among a number of other worlds, special attention is usually paid either to potentially habitable planets with comfortable conditions and moderate climate, or on the contrary, very dangerous objects that stand out from the general background. However, there is a third category. These are anomalous celestial bodies that exhibit strange behavior that is sometimes difficult to explain scientifically. Such objects defy our knowledge and deserve special attention, and the next world belongs to them. 2009. The Kepler 413 System Environment. An unknown object passes between our planet and a distant star, diminishing its brightness for a moment. Astronomers, who believe this event to be a regular transit of an exoplanet, report the discovery of a new celestial body. High-precision calculations can even determine its parameters. The planet turns out to be a cold giant with a mass of about 25 Earth masses and a radius about 40% that of Jupiter. However, the next expected transit did not occur until 180 days later. The planet, so clearly visible in the old data, seemed to vanish without a trace. The mysterious phenomenon can be explained by a dark spot in the photosphere of the star or a giant field cloud moving near it. But these hypotheses were completely disproved when, after 800 days, the mysterious objects returned as suddenly as it disappeared. The supposed planet eclipsed the disk of its parent star 5 times before disappearing again. However, a clue has already been found. It turns out that Kepler 413b's orbit is very unusual. The celestial body is near the double focus and is 0.36 AU away from the common center of mass of the system. Its orbit is subject to constant gravitational perturbations, and the changing attraction of 2 neighboring stars significantly changes the plane of the orbit, causing cyclic oscillations. When the deviation reaches a maximum, the target leaves the field of view and then returns to it. Calculations show that the orbit of Kepler 413b changes with a period of about 11 years, deviating from the average value of 2.5 degrees in either direction. The planet's own rotation axis also changes its position significantly. Its maximum angle of inclination is 30 degrees. Combined with the marked eccentricity of the orbit and its periodic displacement, this results in a bizarre variation of climatic conditions on the surface. The region receiving the maximum amount of light from the parent star is constantly shifting from the equator to the poles and back again, resulting in dramatic temperature variations. It is likely that this process generates huge hurricanes of planetary scale, the size of which could exceed Jupiter's Great Red Spot. Air currents can carry ice clouds at a speed of several kilometers per second, gradually losing stability and collapsing. Meanwhile, collisions and deformation of vortices are capable of creating grandiose atmospheric emissions, which are able to overcome the gravity of the planet and reach the open space. According to calculations, they spend some time there before being pulled back by gravitational forces. All these incredible phenomena make the planet a very inhospitable place. But even that may seem like a peaceful island compared to the future world. 190 light-years from Earth. System environment HD 806-6. In the vicinity of this yellow dwarf, with parameters remarkably close to the Sun, is a planet with a very variable climate. Like a giant comet, it is rapidly approaching its main target, burned by the hot rays of its corona, or moving away to the periphery of the system. SE is a gas giant with 4 times the mass of Jupiter. The radius is slightly different from that of Jupiter. At the farthest point of its orbit, the planet is 0.88 AU away from its parent body and receives about as much heat from it as the Earth receives from the Sun. It is believed that at present, clouds consisting of water vapor droplets, ice crystals, or even quartz microparticles are condensed in its atmosphere. And the surface temperatures of the gas giant's hypothetical satellites can reach Earth-like values. However, as the planet approaches the star, its conditions change very quickly. In 55 days, the distance between the two decreases by a factor of almost 30, while the energy flow of the star increases by a factor of 800. Observations show that at the lowest point of its orbit, the temperature of the exoplanet increases about 2 times in just 6 hours, from 500 degrees to 1200 degrees. Such sudden changes lead to strong hurricanes that can reach speeds of up to 5 kilometers per second. The atmosphere of the gas giant absorbs an incredible amount of heat and expands so rapidly that it creates shock waves that can circle the entire planet several times. Water vapor breaks down into oxygen and hydrogen under the influence of temperature, and quartz crystals vaporize without leaving a trace, but then condense back into giant sand clouds. HD 80606b appears to be the only planet in its system. The gravity of another nearby star not only changed its orbit, but also brought chaos to the protoplanet's disk. Therefore, the chance of encountering large objects nearby is very small. However, destabilization of a planetary system due to the interaction of celestial bodies is not that rare. 1530 Earth color years. Neighboring regions of the Kepler-36 system. The central object of this system is a yellow subgiant. Its mass is close to the solar mass, and its radius is 62% larger than that of our star. 2 planets, a rocky super-Earth and a hot mini-Neptune, are orbiting rapidly around the star. Every 97 days they come critically close, only 1.9 million kilometers, about 20 times the minimum distance between Earth and Venus. At such times, their mutual attraction becomes the cause of global cataclysms. However, a few days pass, and the celestial bodies diverge again until the next resonance. According to calculations, the gravitational interaction between the planets at their maximum approach is about 13 times greater than that between the Earth and the Moon. This effect should be particularly noticeable on the surface of the rocky planet. Its shell can crack and change under titanic forces. Incredibly powerful earthquakes occur. The resulting rifts can be hundreds of kilometers long and cause several giant volcanic eruptions. It is likely that some regions of the planet did not have time to cool down for such a short period of relative calm, and there is always a bubbling sea of hot magma. The reasons for the formation of such an unusual system are still controversial. It is now known that the super-Earth, named Kepler-36b, is located at a distance of 0.12 AU from its parent star and makes a complete revolution around it in 14 days. Its mass is 3.8 times the mass of the Earth, and its radius is 1.5 times the size of our planet. The object is calculated to have a temperature of 980 Kelvin, or just over 700 degrees Celsius, and its average density is about 30% higher than Earth's. Based on this information, it is suggested that the celestial body may be a Croton planet, the core of a gas giant that has lost its atmosphere. Such objects contain many heavy metals, such as iron and lead, as well as sulfur and silicon compounds. It is likely that the light elements that once formed the dense shell of the celestial body could have escaped into space under the influence of the stellar wind. Also, keep in mind the gravitational pull of another planet that can help the process. The name of this object is Kepler-36 Coulomb, and it is believed to belong to the category of hot mini-Neptunes. The celestial body moves in a nearly circular orbit with a radius of 0.13 AU and makes a complete revolution in 16 days. Its mass is 7 times larger than our planet, and its radius is 3.7 times larger than Earth. Because of its proximity, the temperature of the object is also very high, at 928 Kelvin, or 655 degrees Celsius. According to current ideas about the structure of exoplanets, this celestial body is surrounded by a dense, multi-layered atmosphere composed mostly of nitrogen, hydrogen, and helium. As the depth increases, the pressure inside the gas shell increases, and it gradually turns into an ocean of supercritical fluid surrounding the solid core. Meanwhile, under certain conditions are possible and truly fantastic phenomena. For example, the gravity of a more massive planet has the potential to take satellites away from its smaller companion, and tidal stress can destroy them to form vast asteroid streams. In addition, the mutual gravitational influence of the two planets deforms their orbits, changing the eccentricity and other parameters. Because of this, the entire system behaves erratically and unpredictably, and its evolution cannot be calculated for any long time. Modeling shows that with 91% probability, both planets will collide with each other within the next 70 million years, generating hundreds of thousands of debris that will scatter throughout the planetary system, thereby further increasing the chaos within it. Perhaps such large-scale cataclysms have already happened more than once in a neighboring system. 434 light-years from Earth. 4 astronomical units from a young sun-like star is a stunning object informally known as Super Saturn. It is a brown dwarf, or a large gas giant, with a mass of about 20 Jupiters. Observations show that it is a young planet, about 15 to 16 million years old, and still forming. Most of its atmosphere consists of hydrogen and helium, and inside is a massive metallic core. This object is surrounded by a system of rings, much like Saturn, but of much more imposing size. No fewer than 37 distinct rings have been identified from the transit. In addition, the outer radius of the largest of them reaches about 0.6 AU. This is comparable to the size of the orbit of Venus, and about 640 times the radius of Saturn's rings. According to calculations, the total mass of the planet's circular disk exceeds that of Earth, and its behavior shows signs of chaos. Mathematical modeling shows that such structures are unstable and gradually collapse. Some of their particles lose speed and fall to the planet. Others, on the contrary, accelerate and leave the saucer for good. However, this process is much longer in time and may take several 100 million years. Also, in the system of rings was recorded a large gap with a radius of about 0.4 astronomical units, which is considered indirect evidence of the existence in this area of an exosatellite with a mass of about 80% of the Earth. According to modern ideas about the physics of cosmic bodies, it is such an object that is able to clear its orbit from small debris, forming a wide gap in the ring-shaped structure. In addition to him, observations indicate the presence of at least 2 more celestial bodies, each of which has a mass of about 30% of the Earth's and is located at a distance of about 0.25 astronomical units from the center of the brown dwarf. By analogy with known to us large planets, can be assumed that in total, within the gravitational influence of the central object, can be located several hundred exosatellites, including quite massive. Modeling of such a system, taking into account radiation from the parent star, heat flow from the giant planet, and tidal influences, shows that the temperature of its constituent celestial bodies can approach comfortable values. One can only imagine how fascinating the night sky is from the surface of such an exosatellite. At this distance, the brown dwarf occupies an area of the sky 70 times larger than the full moon, and its soft glow can dispel darkness and turn night into a hazy twilight. Instead of a multitude of stars, huge halos of light cross the planet's sky from horizon to horizon. At the same time, the ejective forces of a nearby massive body could cause many eruptions on the surface of the satellite, and its supposed ocean could cover the Earth with giant waves. The width of the tidal zone in such conditions can reach hundreds of kilometers, which allows us to consider it a unique climatic zone, something between the land and the ocean floor. However, it is worth remembering that such structures tend to be unstable and quickly change their appearance beyond recognition. At present, it is difficult to say how long we will be able to admire the giant rings and what will become of them in millions of years. Deep space is full of mysterious and surprising objects. They appear before us in the form of many photographs and a great deal of information, little by little revealing their secrets to all human curiosity. At the same time, each discovery raises new questions, and that means that the learning never ends.